Let's begin by exploring the fundamental concept of titration. Titration is a common laboratory technique in chemistry used to determine the concentration of a solution. By gradually adding a solution of known concentration called the titrant to a solution of unknown concentration, we can observe the reaction between the two. The process continues until the reaction reaches its endpoint, which is often indicated by a color change. This method is essential for analytical chemistry, allowing scientists to precisely measure the amount of a substance in a sample. Titration is widely used in various fields from pharmaceuticals to environmental science, making it a cornerstone of chemical analysis. Titration is favored in laboratories because it provides accurate and reliable results. Whether you're testing the acidity of a solution, determining the purity of a chemical, or analyzing water quality, titration offers a straightforward approach. Its precision comes from the careful measurement of volumes and the clear endpoint, which can be visually detected. This makes titration an invaluable tool for chemists and researchers who need to quantify substances with confidence. The technique's versatility and effectiveness explain why it remains a staple in scientific investigations around the world. Every titration, the titrant plays a crucial role. This is the solution with a known concentration that is added to the analyte or the solution being tested. The titrant is carefully measured and delivered, usually from a burette, to ensure precision. By knowing the exact concentration and volume of the titrant used, chemists can calculate the concentration of the unknown solution. The choice of titrant depends on the type of reaction and the substances involved, making it important to select the right chemical for each titration experiment. The analyte is the solution whose concentration you want to determine. It is placed in a flask and the titrant is gradually added to it. The reaction between the titrant and analyte is monitored closely, often with the help of an indicator. The analyte's properties and the reaction it undergoes with the titrant are key to achieving accurate results. Understanding the nature of the analyte helps chemists choose the right titrant and indicator for the experiment, ensuring the titration process is both effective and reliable. Indicators are substances that signal the endpoint of a titration, usually by changing color. The choice of indicator depends on the type of reaction and the pH range over which the color change occurs. For acid-base titrations, common indicators include phenolphthalein and methyl orange. The right indicator ensures that the endpoint is clear and unmistakable, which is vital for accurate measurements. Indicators make titration accessible and straightforward, even for those new to laboratory techniques. There are several types of titration, each suited to different chemical reactions. The most common are acid-base titrations, which involve the reaction of an acid with a base. Other types include redox titrations, where oxidation and reduction reactions occur, and complexometric titrations, which involve the formation of a complex between the analyte and titrant. Each type requires specific reagents and indicators, but the underlying principle remains the same: measuring the amount of titrant needed to reach the endpoint. Acid-base titrations are perhaps the most familiar type. In these experiments, an acid reacts with a base, and the endpoint is detected with a pH indicator. The process allows chemists to determine the concentration of either the acid or the base in a solution. By carefully measuring the volume of titrant added, the unknown concentration can be calculated using stoichiometry. This method is widely used in educational labs and industry alike, thanks to its simplicity and effectiveness. Redox titrations involve oxidation-reduction reactions, where electrons are transferred between substances. These titrations are used to analyze compounds that can act as oxidizing or reducing agents. The endpoint is often detected by a change in color, either from the reactants themselves or with the help of an indicator. Redox titrations are essential in fields like environmental chemistry, where they help determine the presence of substances such as iron or chlorine in water samples. Complexometric titrations are used to determine the concentration of metal ions in a solution. These titrations involve the formation of a complex between the metal ion and the titrant, often using a reagent like EDTA. The endpoint is usually indicated by a color change, thanks to a special indicator that reacts with the metal ions. This technique is particularly useful in water hardness testing and in the analysis of industrial samples. Precipitation titrations are based on the formation of an insoluble product, or precipitate, during the reaction. This type of titration is often used to determine the concentration of ions such as chloride or sulfate. The endpoint is detected when no more precipitate forms, sometimes with the help of an indicator. Precipitation titrations are valuable in environmental testing and quality control in various industries. To perform a titration, you'll need some basic laboratory equipment. The most important tools are the burette, which delivers the titrant, and the flask, which holds the analyte. You'll also need a pipette for measuring precise volumes and an indicator to signal the endpoint. Proper equipment ensures accuracy and safety during the experiment, making it essential to use clean and calibrated tools for every titration. Burette is a long, graduated tube with a tap at the bottom, used to deliver the titrant in a controlled manner. Its precise graduations allow for accurate measurement of the volume added. By carefully reading the burette before and after the titration, chemists can determine exactly how much titrant was used. This precision is crucial for calculating the concentration of the analyte. Before starting the titration, the analyte must be prepared. This usually involves measuring a specific volume of the solution and placing it in a clean flask. Sometimes the analyte is diluted to ensure the reaction proceeds smoothly. An indicator is then added to the flask, setting the stage for the titration to begin. Proper preparation is key to obtaining reliable results. With the analyte prepared and the burette filled with titrant, the titration can begin. The titrant is slowly added to the analyte while stirring the solution. The chemist watches for a change in the indicator, which signals the approach of the endpoint. Adding the titrant gradually ensures that the reaction is controlled and that the endpoint is not missed. Endpoint of a titration is the moment when the reaction is complete, often indicated by color change in the solution. This change means that the amount of titrant added is just enough to react with the analyte. Detecting the endpoint accurately is crucial for precise calculations. Some titrations use electronic sensors to detect the endpoint, but visual indicators remain popular for their simplicity. Once the endpoint is reached, the volume of titrant used is recorded. Using the known concentration of the titrant and the measured volume, chemists can calculate the concentration of the analyte. This calculation often involves simple stoichiometry, relating the moles of titrant to the moles of analyte. Accurate calculations are essential for reliable results in any titration experiment. Like any scientific technique, titration is subject to potential errors. Common sources include inaccurate measurements, improper mixing, or misreading the endpoint. Using clean, calibrated equipment and following proper procedures can minimize these errors. Being aware of possible mistakes helps chemists improve their technique and obtain more reliable results. To achieve the most accurate results, chemists take several precautions during titration. These include using freshly prepared solutions, calibrating equipment, and performing multiple trials. Consistency in technique and careful observation are key. By refining their approach, scientists can ensure that their titration results are both precise and reproducible. Titration is not just a classroom experiment, it plays a vital role in many industries. In pharmaceuticals, it's used to ensure the correct dosage of active ingredients. In food production, titration helps monitor acidity and quality. Environmental scientists use titration to analyze water samples for pollutants. Its versatility and reliability make titration a trusted method in countless professional settings. Titration is a staple of chemistry education, introducing students to essential laboratory skills. By performing titrations, students learn about chemical reactions, measurement, and data analysis. The hands-on nature of the experiment makes it engaging and memorable. Titration also teaches the importance of precision and careful observation, skills that are valuable in any scientific discipline. Titration is crucial in monitoring environmental health. Scientists use it to measure pollutants in water, soil, and air. By determining the concentration of harmful substances, titration helps guide environmental policies and cleanup efforts. Its accuracy and reliability make it an indispensable tool for protecting our planet and ensuring public safety. The pharmaceutical industry, titration is used to analyze the purity and concentration of drugs. Accurate measurements are essential for ensuring that medications are safe and effective. Titration helps manufacturers comply with strict regulations and maintain high standards of quality. Its role in drug development and quality control cannot be overstated. Titration is widely used in the food industry to monitor acidity, salt content, and other chemical properties. These measurements help ensure that food products meet safety and quality standards. For example, titration can determine the acidity of vinegar or the vitamin C content in juice. Its reliability makes it a preferred method for food analysis. Titration is essential for analyzing water quality. It helps detect the presence of contaminants like chlorine, hardness ions, and heavy metals. By providing precise measurements, titration supports efforts to ensure safe drinking water and protect aquatic environments. Its role in public health and environmental monitoring is invaluable. Quality control laboratories rely on titration to verify the composition of products and raw materials. By ensuring that substances meet specified standards, titration helps maintain consistency and safety in manufacturing. Its precision and reliability make it a cornerstone of quality assurance processes across many industries. Modern laboratories often use automated titration systems to increase efficiency and accuracy. These systems can perform multiple titrations simultaneously, reducing human error and saving time. Automation also allows for more complex analyses and better data management. As technology advances, automated titration is becoming increasingly common in research and industry. After a titration, the collected data must be analyzed to draw meaningful conclusions. This involves calculating concentrations, plotting titration curves, and interpreting results. Accurate data analysis is essential for making informed decisions in research and industry. Modern software tools can assist with calculations and visualization, making the process more efficient. Titration curve is a graph that shows how the pH of a solution changes as titrant is added. These curves help chemists understand the reaction and identify the endpoint more precisely. By analyzing the shape of the curve, scientists can gain insights into the properties of the analyte and the reaction mechanism. Titration curves are especially useful in research and advanced studies. Selecting the appropriate indicator is crucial for a successful titration. The indicator must change color at the correct pH or reaction point. Factors such as the type of titration and the expected endpoint influence this choice. Using the wrong indicator can lead to inaccurate results, so chemists carefully consider their options before beginning the experiment. Safety is always a priority in the laboratory. When performing titrations, chemists wear protective gear such as gloves and goggles. They handle chemicals with care and follow established protocols to prevent accidents. Proper waste disposal and equipment cleaning are also important. By maintaining a safe environment, scientists can focus on obtaining accurate results. Even experienced chemists can make mistakes during titration. Common errors include adding titrant too quickly, misreading the burette, or using the wrong indicator. Being aware of these pitfalls helps prevent them. Careful technique and attention to detail are the best ways to avoid mistakes and ensure reliable results. If something goes wrong during a titration, there are steps you can take to troubleshoot. Double-check your equipment, make sure solutions are fresh, and review your procedure. Sometimes, repeating the experiment or consulting a colleague can help identify the problem. Troubleshooting is a valuable skill that helps chemists improve their technique and achieve better results. Accurate record-keeping is essential in titration. Chemists document the volumes used, the appearance of the endpoint, and any observations during the experiment. Detailed records allow for reproducibility and help identify trends or errors. Good documentation is a hallmark of professional scientific work. After completing a titration, it's important to review the results. This involves checking calculations, comparing data from multiple trials, and considering any anomalies. Reviewing results helps ensure accuracy and provides insights for future experiments. It's a critical step in the scientific process. Once the data has been analyzed and reviewed, chemists report their findings. This may involve writing a lab report, presenting results to colleagues, or publishing in a scientific journal. Clear communication of results is essential for advancing knowledge and sharing discoveries with the wider community. Titration has a rich history dating back to the 18th century. Early chemists developed the technique to analyze acids and bases, paving the way for modern analytical chemistry. Over time, titration methods have evolved, becoming more precise and versatile. Understanding the history of titration provides context for its importance in today's laboratories. Many renowned chemists have contributed to the development of titration techniques. Figures like Anton Lavoisier and Robert Bunsen made significant advances in analytical chemistry. Their work laid the foundation for the precise methods used today. Learning about these pioneers inspires appreciation for the science behind titration. Today, titration continues to evolve with new technologies. Digital burettes, automated systems, and advanced software have made titration faster and more accurate. These innovations allow for high-throughput analysis and better data management. Staying up to date with modern techniques ensures that chemists can tackle new challenges with confidence. Research laboratories use titration to explore new chemical reactions and develop innovative products. Whether studying environmental samples or creating new pharmaceuticals, titration provides reliable data. Its adaptability makes it suitable for a wide range of scientific investigations, supporting discoveries across disciplines. Future of titration looks promising, with ongoing advancements in automation, miniaturization, and data analysis. Portable titration devices and real-time monitoring are becoming more common, expanding the technique's applications. As science progresses, titration will continue to play a vital role in analytical chemistry and beyond. Titration impacts society by ensuring the safety and quality of products we use every day. From clean water to safe medications, titration supports public health and well-being. Its role in environmental protection and industry highlights the importance of scientific methods in our daily lives. Mastering titration requires practice and attention to detail. Students and professionals alike benefit from hands-on experience, learning to handle equipment and interpret results. Developing these skills opens doors to careers in science, medicine, and industry, making titration an essential part of scientific education. While titration may seem like a laboratory-only technique, its principles are present in everyday life. For example, testing pool water for chlorine or checking the acidity of homemade vinegar involves similar concepts. Understanding titration helps us appreciate the science behind many routine tasks and products. Sum up, titration is a powerful analytical tool that enables chemists to determine the concentration of unknown solutions with precision. Its applications span education, industry, and environmental science. By understanding the principles and mastering the technique, anyone can unlock the potential of titration in scientific discovery and everyday life. Titration stands as a testament to the power of careful measurement and observation in science. Its enduring relevance in laboratories and industries worldwide highlights its value. Whether you're a student, researcher, or professional, understanding titration opens up new possibilities for exploration and innovation in chemistry.